Welcome to the third part of Building Robots, System Integration. My name is Gaspar Škulj from University of Ljubljana, and today we will learn about a mobile robot with differential drive. We will start with robot configuration and how it can be built. Next, we will look at its kinematics and define this week's project assignment. A mobile robot is a mechatronic system that can move in its environment without having a fixed connection point. It therefore requires to carry its own power source. There are many types of mobile robots, differentiated by the way they achieve their movement, their type of locomotion. We will focus on the simplest and most accessible type of a mobile robot. That is, a wheeled mobile robot with differential drive that has two drive wheels and usually a support. This type of ground robots are usually limited to relatively flat surfaces and slower speeds. However, they are very agile and can turn on a spot. Primary function of a mobile robot is to move around based on manual control, predefined path, or from point A to point B, finding its own way. While moving, they can carry a load that could also be an observation equipment or a tool. To achieve movement, the robot has two drive wheels, and each wheel rotation is independently controlled. If the two wheels rotate with exactly the same speed, the robot will move in a straight line. Otherwise, it will travel on an arc. The difference between rotation speeds of the two wheels determines direction of travel, and that is why it is called a differential drive. The same concept also applies if instead of wheels, the robot would use two similarly oriented propellers or tracks. A mobile robot with a differential drive can be built in various different and interesting ways, mostly dependent on the robot's function. The function of our robot is to be an educational example. This means that we as students want to see its components and have the opportunity to easily modify them. So the robot looks different than commercial robots and has parts that are not optimized for physical performance, but for use flexibility. Because we want our system to be modular, the robot is built with two identical servo motors with large wheels and additional support. And servo motors are also modular, consisting of three parts: the base, the gearbox, and the output shaft. Building blocks for the base are GEMS PCB modules. Each module has its specific function. Green PCB Emerald is the battery power supply, red PCB Ruby is for sensoric, blue PCB Sapphire for communication, and white PCB Diamond for control. They are connected in a circle with four flat cables that connect each board to the battery and the CAN bus. The modules are positioned between two 3D printed plates held together with four connectors. And one of the plates also holds a DC motor with a gear and encoder. The gearbox attaches to the base and has 5 compound gear pairs with reduction ratio of 3:1 on 2 steel axles. This gives us a high reduction ratio of 243:1. The output shaft rotates slowly and has a lot of available torque. For the torque to be transferred to the drive wheel, the output shaft is fitted with custom-built bearing. This again, decision based on educational value, being able to demonstrate the working of an important mechanical component. Now that we have two servo motors, we can connect them so that the wheels share the same axis of rotation. The robot would also work if the output shaft were at an angle. Just worse, because wheels would have to slip for the robot to move straight. Because the center of mass of the servo motor is close to the axis of rotation, our robots need an additional support so that the body doesn't rotate while it tries to move forward. As the support is only on the back side, the robot shouldn't decelerate too fast, otherwise it will roll over. With a constructed mobile robot with a differential drive, we can discuss its kinematics. That means we want to describe its movement in a more formal way with equations. There are two possible questions about robot's movement. First, where will robot move with certain rotation speeds for its two wheels? Second, what could rotation speeds of the two wheels be to get in a certain position? For the first question, we need forward kinematics, and for the second, inverse kinematics. We assume the robot moves on a perfectly flat surface and that wheels don't slip. Forward kinematics is not complicated and is based on a set of similar triangles. We start with information about rotation speeds of both wheels and the distance between them. As the result, we want linear speed and rotation speed for robot's center of mass. First of all, we calculate linear speeds for each wheel based on their diameter. Next, the linear speed of the robot is average linear speed of both wheels. And the robot's rotation speed is based on the difference between both speeds and the distance between the two wheels. Instant center of rotation is also important results, as it tells us around which point the robot is rotating at the moment. Now that we have this information, we can calculate where the robot will be in X amount of time by integration. Inverse kinematics is the other way around. We start with information where the robot is now and should be in X amount of time. Then we want to know what should the rotation speeds of the wheels be in time to achieve the desired position. The problem is much harder because wheeled mobile robot with differential drive has constrained movement. It is a non-holonomic system. It can only move forward, backward and rotate, but it can't move sideways. For this case, we can make the question of inverse kinematics a lot easier if we simplify the question to what should rotation speeds of the two wheels be for the robot to have a certain linear and rotational speed. There are three distinct cases we can look at. First, only linear motion and no rotation. Second, no linear motion and only rotation. And third, linear motion and rotation. For each of these cases, we can easily calculate the required velocities. Movement from point A to point B is composed from many instances of these three cases. At this point, we have enough information about kinematics for a mobile robot with differential drive. Your task for this week is to create another Hello World example, but for forward kinematics. When we are controlling our mobile robot by setting speed for each wheel, it would be informative if the robot would have information about its current translation and rotation speed. Additionally, we would like to know the radius of the arc the robot is moving on. Create a program for a ESP32C3 or S3 microcontroller with a function that calculates translation speed, rotation speed, and path radius for a measured speeds of left and right DC motor of the mobile robot. Don't forget to consider the gearbox reduction ratio and wheel diameter. For the test, call the function and print the results over serial communication for several examples. First, speed of both motors is 0 Hz. Second, speed of both motors is 40 Hz. Third, speed of one motor is 20 Hz and speed of the other is minus 20 Hz. Fourth, speed of one motor is 40 Hz and speed of the other is 20 Hz. A wheeled mobile robot with a differential drive is a robot with a simple configuration, but nevertheless requires a lot of different components to be connected in a correct way. Understanding of the robot's kinematics is especially important to successfully design and control it. The robot we were studying also demonstrates the use of modularity concept and 3D printing process to create all the mechanical connections that you can modify to change the robot's characteristics. Thank you for watching.